Today we will be doing chapter 10, which is circles. So what is a circle? I'm sure you all know by now how to identify a circle. So a circle is a collection of all points in a plane. By plane, we refer to a two-dimensional shape. So circle is a 2D figure. And what's so special about it? This boundary, the boundary of this shape that you see on your screen is what we call a circle. Here we have a center. So all circles are referred to with respect to their centers and their radii, which is the plural of radius. Radius is a constant distance between the center of a circle and the point on the periphery or the circumference of the circle. This boundary that you see over here, this is the circumference or the periphery of the circle. So this distance is always constant. So whenever we talk about the trajectory of a point which is at a constant distance from another point, we refer to it as a circle. So this is my fixed point, and from here you move the same distance every time in different directions. And when you join all such points, what you get is a circle. So these are the parts of a circle. Then if I join any two points on the circumference of a circle, I get a chord. This line segment is called a chord. It is of a fixed length. Okay, it's not a line, it is a line segment. And then we have diameter. The diameter is the longest chord of a circle. It is also a chord. I hope you can see that because it is joining the 2 points. It is joining the 2 points located on the circumference of my circle. In fact, there is a relation which relates the diameter to the radius of a circle, and that is diameter is equal to 2 times the radius of a circle. It is the longest chord of a circle, as you can see, and the only way by which you can reach from one point on this circle to another point by covering the longest distance is the diameter. Now, I give you a minute to spot 5 circles around you, and let's see how many can you spot. So there are different circles around us, like we have bangles, we have rings, we have the wheels of our cars. What else do we have? Nowadays, you would also be aware of Olympics. So the symbol of Olympics, it consists of 5 rings. So those are also circles only. And in fact, you'll be amazed to know about encyclopedia, the book of knowledge. In fact, it also means the circle of learning. So these are the parts of a circle. Just remember them: center, radius, chord, and the longest chord being diameter. Now, if you've understood these parts, we'll now move on to a very important part, which is the tangent to a circle. Tangent and secant. So to understand that, you need to consider a circle and a line. So let's say this is my circle over here and this is my line. What is the name of this line? PQ. So there can be 3 possibilities when I'm considering the case of a circle and a line. So the first case is that this line does not touch this circle at any point, as you can see in this figure as well. Now, in such a case, we can say that the line PQ and the circle do not have any common point. If they do not have any common point, it obviously means that PQ does not intersect with the circle, or PQ is non-intersecting with respect to the circle. So this is the first possibility. Now we move on to the second possibility. So it might happen that your line actually touches the circle, that too at 2 points, A and B. So when we have such a case where your line PQ touches the circle at 2 points, so there are 2 common points, then we call such a line PQ as a secant of the circle. Okay, this is very important. What do we mean by a secant? To understand a secant, you have to consider a line and a circle. But a very special case arises when this line touches the circle at 2 common points. That is when that line is called the secant. Now that you've understood secant, we move on to tangent. So this is a third and final possibility. So we can have a line which touches the circle but at only one point. Okay, and in that case this point over here is point A. So when there is only one common point, you call it what? A tangent. A quick recap. What if we have two common points? What do we call the line PQ then? We call it a secant. So this is an important difference between a tangent and a secant, that in both the cases your line is intersecting the circle, but in case of tangent that point of intersection is only one, whereas in case of secant there are two such points. What about the case of zero common points? It obviously means that the line does not intersect with the circle, or we can say that the line is non-intersecting with respect to the circle. So now time for a fun activity. So you have to take a circular wire. It doesn't matter if it's not circular, wires are easily bent. So you make it circular, make a loop out of it, and then take another wire, take a straight wire AB then. Okay. So say this is your circular wire, and then you take a straight wire AB. Put this AB on this circular wire and fix it on this point P over here. Okay, just keep this point fixed. It's like the pivot of your activity now. Okay, now what you need to do is take this system, put it on your table, and then rotate this wire AB. Like in your board games you must have played, there are games, right? So you just have to rotate it. You can rotate it in this direction first. Okay, so first we are going in this direction. This is the anti-clockwise direction, and then every time you rotate, note the points of contact between AB and your circle. So let's say you rotate it once and you get this point Q1. You rotate it again, you get the point Q2. Again, you get Q3. So just keep marking these points. Then we have ultimately this point diminishing to P only. So basically what we noticed here was that when we are rotating this wire AB in a circular fashion, but in anti-clockwise direction, keeping this point P fixed, then we are getting different points. And what's so special about these points? That as you keep on rotating in this direction, these points keep coming closer and closer to which point? To the point P. Ultimately, they diminish only. It just becomes point P. Everything boils down to the point P. And what can you say about this A dash B dash line? So this is basically my circle, and here we have this line over here, A dash B dash, and how many common points do we have? Only one, which is P. So what is so special about such a line? It is called the tangent to a circle. So A dash B dash is a tangent to the circle in this case, and that common point over here is P. Now right now we just rotated this wire AB in the anti-clockwise direction. What if I do the process, but this time in the clockwise direction? So let's say you get the point R1, then you get point R2, then R3, and ultimately you get this A double dash B double dash. Okay, it doesn't stop here. You may continue rotating it in the clockwise direction, and ultimately you will notice that even in that case all your points will diminish. You'll just get one common point, that is P. And that means that at one point of a circle there can only be one tangent. Okay, so if this is your circle and this is one particular point that I'm focusing on, then there can only be one tangent to it. A circle in fact has infinite tangents because it has infinitely many points. So a circle has infinite tangents, but we are talking about the tangent to a circle at a particular point. So that is only one tangent. Alright. And in fact this common point has a special name to it, which we will see further also. It's actually called the point of contact. So in this case P is that point of contact, this point P. So a circle actually has infinitely many points, and hence a circle has infinite tangents. But if we put our focus on only one point on the circle, then we can have only one tangent. And in fact this point, this common point that we are referring to, has a special name. which we'll be discussing again as well, and that is actually called the point of contact. So here this point P is the point of contact. So this is just a summary. So when we did this activity, what did we realize? That no matter what we do, okay, if I'm keeping this point P fixed on my circle and I'm rotating this wire, be it in anti-clockwise direction, be it in clockwise direction, I'm always ending up at a stage where I'm only having one point. So in the end, all points they just coincide and we're just left with this point P. So from this activity, we can draw one conclusion, which is that tangent is a special case of secant. I hope you remember what secant was. So secant was a line which was meeting the circle at two common points. So basically for a tangent, we can say that those two common points are coinciding. So that makes it a special case of a secant only. Then time for activity number 2. So take a paper, draw a circle, okay, and then make a secant PQ of the circle. So what was a secant? Where there were how many points, common points? 2 of them. So take a circle and tell me, is PQ a secant, or is it a tangent, or is it a non-intersecting line? Well, it is definitely a secant because there are 2 common points. Then you have to draw various lines parallel to this secant, okay, on either sides of it. And let's say I draw one time this over here, then next time on the other side. So what you notice here is that all these lines are actually turning out to be parallel to one another. That you can make out from the figure itself. So let's continue drawing these lines. This is a very easy activity. And ultimately, what you notice over here is that this was my initial secant, right? PQ. And if I don't consider the line, but the line segment inside the circle, in parts of a circle, we discussed that any line segment, mind you, the emphasis on segment, any line segment which has, which basically joins any 2 points on the circumference of a circle. Such a line segment was what we were calling a chord. So basically, if you notice this distance, it is actually a chord of the circle. This is also a chord of the circle. Now, as I move away, you can make use of a ruler. You can measure these chords, and you'll realize that as we move away from this longest secant that we have drawn, the length of the chord is decreasing. Okay, this keeps on decreasing, and ultimately, what we get on drawing lines is we don't even end up with a secant. What we get is a tangent to a circle. Because what do you see here? How many points are there? Common points? Only 1 instead of 2, which means this P double dash Q double dash is no longer a secant but a tangent. And similarly, if I draw this P dash Q dash, that is also a tangent to the circle. So ultimately, we end up getting tangents to a circle if we keep on moving away from the center of the circle, because the length of the chord keeps on decreasing, and ultimately it becomes 0 because that chord, that line segment diminishes to a point. That common point, let me see how much you remember. What did we say about that common point? What is it called? It is called the point of contact. So in other words, you can say that these chords, they keep coming closer to each other. Okay, these distance between any 2 points keeps decreasing. Okay, because this length of chord is decreasing. So once again, what you can say from this activity is that the tangent to a circle is a special case of secant, where the 2 endpoints which used to exist for secants have now coincided to give you just one common point called the point of contact, and thereby a secant converts to a tangent. So we can say tangent to a circle is a special case of secant. From here we can also draw another conclusion that a tangent only has one point of contact with the circle. So a tangent only has one point of contact with the circle. Alright, every time we draw a tangent, we see that there is only one common point, so there is only one point of contact which the tangent would make with the circle. So let's understand this tangent to a circle application via a real life example. So even if you don't have your licenses yet to drive a car or an Activa, you must be knowing how to ride a bicycle, or maybe you would be having some toy cars in your home or something, or you can at least make use of your brain and visualize a wheel which is moving on a road. Okay, it's rotating on a road. So this wheel is also a circle if you look carefully. This being its center, this being the boundary being the circle actually, and this is the interior of a circle, this air is the exterior of the circle, and what you notice here is a road. So at how many points is this road going to touch my wheel? At any instant of time. At any instant of time, the road will touch the wheel. So the road touches wheel at how many points? At only one point. That is to say that there is only one common point between the road and the wheel at any instant of time. Okay, I'm not saying the entire time, but at only one instant of time. So we can also say that road in a way is a tangent to your wheel, because road is like a line and wheel is like a circle. And here there's only one common point. We can call that point P. And what do we call this point P? We call this the point of contact. So that brings us to theorem 1. So the tangent at any point of a circle, so this is your circle, this is your tangent over here, xy, right? Xy is your tangent. It is perpendicular to the radius. What is the radius over here? The line segment which joins the center and a point on the circumference of a circle. So that is OP in this case. Through the point of contact, what is the point of contact over here? That is point P. Alright, so you've been provided with a circle having center O, okay, and we take a point on its circumference P, and it's actually the point of contact between the tangent xy and this circle with center O. If you join O and P, what you get is the radius of the circle OP. Now what I want you to do is take a point on this tangent xy. Okay, this point better lie on this tangent xy, and the number 2, the thing number 2 that you need to be very careful of is that this point should not be coinciding with the point P. It should be some point other than P, and it should be lying on this tangent xy. So let's say such a point is Q. You can join these points O and Q by means of dashed lines. And now what we need to prove is that this distance OP, which is the radius of the circle, it is perpendicular to the tangent which is xy. So why are we not taking this point Q anywhere else? Why only on the tangent? Because if we take it outside, then we can't really make much use of it. And if we take it inside, then it will become a secant. Alright, so we have to take it over here. And if I take it on this circle, then what would happen? It would become just a radius of the circle, right? So what we notice from the figure itself is that OQ is actually longer than your radius of the circle OP. In fact, it's not just the case with point Q. If you take other points also on this tangent, okay, say Q dash, R dash, etc. As long as that point is not point P, you'll realize that the distance between point O and that point will always be greater than this radius OP. Except when it becomes equal, OP equal to OP, it means that your radius is actually perpendicular to the tangent. Okay, so when you measure these distances, you'll realize that OP is the shortest of all distances. Okay, by all distances, we are measuring which distances? The distances between the center and the point that we're taking on the tangent to the circle. So the shortest distance would arise when we take OP. So OP is perpendicular to XY. Okay, so OP is perpendicular to XY, and we can have a few remarks on this theorem, that this OP perpendicular to XY, in such a case OP is also called the normal to a circle. This is also called the normal to a circle. Okay, so it's just another way of calling a perpendicular. You can say in math, normal is synonymous with perpendicular. Okay, then at any one point, you see that there can only be one tangent to the circle, okay, because there's only one point of contact. So it's just a repetition of what we've learned from the previous two activities. Then we have how many tangents can we have from a point on a circle. So again, what does a tangent mean? How many common points? One common point. What do we call that common point? The point of contact. So here there are three possibilities if you want to understand the number of tangents. So case number one, there is no tangent. No tangent means you're considering points, say, inside the circle. Okay, this is the interior of the circle. Now, as long as you're considering these line segments inside the circle, you'll always have two common points. And that makes it a secant and not a tangent. Okay, there is no tangent, instead there is a secant if the points are lying inside the circle. If the point lies on the circle, again, by on the circle, we mean the boundary of the circle, the circumference of the circle, then there can only be one tangent. That's what we discussed from the activities as well, that for a particular point on a circle, there can only be one tangent. There will be one tangent if point lies on the circle. And case number three, what if the point is an external point? It's not lying inside the circle, it's not lying on the circle, it's somewhere in the exterior part of the circle, and let's say that is point P. So what you realize is that from such a point, you can make two tangents to the circle, which will be PT1 and PT2 in this case. So there will be exactly two tangents to a circle for a point lying outside the circle. So here we discussed three possibilities. Okay, so if your point is inside the circle, if it is on the circle, and if it is outside the circle. And you tell me, if it is inside the circle, how many tangents do we have? Zero tangents. If it is on the circle, we've seen this many times, there is only one tangent. And this is something new. If we have an external point, then how many possibilities are there to get the tangents? There are only two tangents which are possible to the circle now. You can remember this flowchart. Then now that we're talking about tangents, and there should be some length also attached to this tangent. So that's exactly what we aim to measure now. So if I give you an external point P and we have this circle, and you know that from an external point, how many tangents can I draw? I can draw two tangents. So in this case, what are those two tangents? PT1 and PT2. So if you want to measure the length of these tangents, what you are essentially going to measure is the distance between this external point P and the point of contact. Which point of contact? Between this tangent and the circle. Okay, point of contact, in fact this term is only used primarily when you are considering intersection between the tangent and the circle. So look for the common point between tangent and circle and measure the distance from that point to this point, external point P, from which you are drawing your tangent. Since we are having two tangents over here, you can find the lengths of both the tangents. They will turn out to be PT1 and PT2 respectively. And what is so special about such lengths of tangents is that the two lengths turn out to be equal. So PT1 is actually equal to PT2. This is very important, and we'll be proving this by means of a theorem also, which follows up next. So length of tangent is PT1, PT2, and both the lengths are equal. So now we move on to the second theorem for the day. The lengths of tangents drawn from an external point to a circle are equal. So consider a circle with center O. Then you tell me, what is the external point over here? Is it P, is it Q, is it R? By external point, we refer to a point which is neither inside the circle nor on the circle. So that is point P. And from this point P, how many tangents can I draw? Two of them. So what are those two tangents? Can we spot them? They are PQ and PR. So what is the point of contact? So basically, whenever we have a tangent and a circle, there is a point of contact, which is basically just one common point. So in this case, that is Q, and here we have it as R. So we have to prove that PQ and PR are equal. So for that, what you need to do is, by dashed lines, join OQ, OP, OR, join all these points. Now comes the main proof. Now angle OQP, which is this angle, and angle ORP, which is this angle, both of them are 90 degree. Okay, angle OQP is equal to angle ORP is equal to 90 degree. Why am I saying this? Because if you remember in theorem 10.1, we said that a tangent is perpendicular to radius of a circle, right? So OQ is what? OQ is radius of a circle, PQ is tangent, OQ is radius. They are perpendicular because theorem 10.1. So that's why I'm able to say that angle OQP is equal to 90 degree. Number 2, you see that PR is a tangent, OR is also a radius. How is it a radius? Because it's joining the center and a point on the circle. So this PR is perpendicular to OR radius by theorem 10.1 again. So perpendicular means what? That this angle ORP is equal to 90 degree. So I hope you get it, how we are getting these angles is 90 degree. Now you have to consider these triangles OQP. Now it is a right angle triangle because if one angle of a triangle is 90 degree, it becomes a right angle triangle. So OQP is a right angle triangle, and if you notice triangle ORP, that also has a 90 degree angle. So both the triangles are right angle triangles. So here we'll try to prove these two triangles congruent now. So you notice that these angles are already equal, right? Angle OQP is already equal to ORP, equal to 90 degree, which is so how. And further, OQ and OR, they are equal in length because radii of a circle. We just discussed that a circle is a boundary basically formed by points which are at the same distance from the center of that circle, and that same distance is called the radius of the circle. So OQ and OR are equal. And if you notice OP, that is like a common side over here. So that's why triangles OQP and triangle ORP turns out to be congruent. The two triangles are congruent to one another, but by which congruency criterion are we saying that? That is your homework, you tell me. Then we know that if any two triangles are congruent, we can say that PQ and PR, these two lengths, they are the corresponding sides of the triangle. They will turn out to be equal. CPCT. What was CPCT? Corresponding parts of congruent triangles. So they are equal if once you've proven the two triangles congruent. So if PQ and PR are equal, so I can also say similarly by making use of CPCT that angle OPQ, this angle, is equal to angle OPR, this angle. Okay, because they are also corresponding angles, so they would also be equal. So if these two angles are equal, it means that OP, this line over here, is actually the angle bisector of angle QPR. So if you look at this full angle QPR, it is basically getting divided into two equal angles, namely OPQ and OPR. So in other words, you can say OP is an angular bisector of angle QPR.